Okay, so now we move to the next part of this lesson, section 2.3. We are going to discuss about elastic energy. Okay, so what do you mean by elastic energy? So basically, when you stretch a string or an elastic string or spring, you realize that when you stretch it, we say there's energy stored in an elastic string or spring. Okay, so look at this. Now over here you can see we have drawn a force distance diagram to show the extension x in an elastic string. Do you see? Now you do realize tension is directly proportional to extension, isn't it? If tension is directly proportional to extension, do you agree with this particular graph? When you draw extension against tension, you need to realize that it is a straight line that passes through the origin. Do you see? So this is a straight line because when you draw this graph t equal kx, okay, so this k value, when you remove the proportional, it's k, and the k value is what we have found as lambda over L, isn't it? T equals the k value is what is lambda over L here, which is completely a constant. So this is basically a y equal mx type graph. So basically it goes through the origin, a straight line with a positive gradient that goes through the origin. So this is really important. The area under the force distance graph is the work done in stretching the elastic string. Okay, so what is the area under the force distance graph? The area under the force distance graph is the work done in stretching the string. Okay, so you can see to find this work done in stretching the string to get this area. So they have found this area using two ways. Okay, they have found this area using two ways. One by using the one by using the area of a triangle, the other one by integration. So let's go with both the ways. Let's try to understand both of them. Okay, so using the formula for area of a triangle, do you see how this works? Area of a triangle is half into base into height, isn't it? So I think you can see here the tension value, they have marked it as lambda x over L. Okay, so the tension is equal to lambda x over L and the extension is x. Basically, the gradient of the graph is lambda over L, isn't it? The gradient of this particular graph is lambda over L. We don't need that at this point. All I need is the x and y coordinate of this point to get the area of the triangle. So half into base into height. Base is x, height is lambda x over L. Okay, so you get here the area under the graph. The work done in taken in stretching the string to an extension x is lambda x square over 2L. Can you see? Also, we can get this result by using integration. So they are integrating. You do realize when you integrate a graph, you get the area under the graph, isn't it? P2. When you integrate, you get the area under the graph. So here we integrate the y variable is t. So they're integrating with respect to with respect to s here. Okay, how does that work here? So when you integrate now, t is a constant. Okay, so we use the letter s here. They're integrating with respect to s like the stretching the string. Okay, so t is a constant which you can take out when you integrate with respect to 1. What do you get here? TDS. Okay, they're just randomly actually using a letter here. Okay, so the limits basically here the s represents the x-axis over here. Okay, so what are the limits you're using here? You're using from 0 to x. The reason that they're not using x here is because your limits also has the letter x. That is why they're using a different letter here. Okay, because your limits, you can see here x limits, the extension limits are from 0 to x. Actually, they have told here extension is s, right? Can you see? They have told here extension is s, represented by the letter s. So the extension limits are from 0 to x. Okay, so t is t, we can write it as lambda x over L. Lambda x over L, actually don't use x, the extension we will use the letter. What are we going to use? Lambda s over L. Are you guys with me? Because we use the extension with the letter s, the extension I will use here is lambda s over L. And the limits are from where to where? 0 to x. And take the constants out. You know the s is the variable, lambda is a constant, natural length is a constant, take them out. Lambda L comes out in the integration. Inside the integration sign, we have s. When you integrate s with respect to s, what do you get? What do you get when you integrate s? You add 1 to the power and divide, right? So s square over 2. Your limits are from 0 to x. Shall we replace? So when you replace, this is going to be x square over 2 minus, you replace s with 0. So do you see that you end up getting again lambda x square over 2L? Okay, so the work done in stretching the string is lambda x square over 2L. So you can see whether you use integration or whether you use the area of the triangle, you get the same answer, the work done. Okay, so then we can write down this summary. So what is the summary over here? The work done in stretching an elastic string or spring of modulus of elasticity lambda from its natural length L to a length L plus x. Do you see? So from the natural length L, you are pulling it to a distance L plus x. So the work done in stretching the string is lambda x square over 2L. The work done in stretching the string is to extension of x is lambda x square over 2L. Are you with me? Where lambda is measured in newtons, lambda is the spring constant, it's measured in newtons, and x and L are measured in meters. The work done is in joules. Okay, so that is another important thing. You are getting the unit of the work done. Work done unit is in joules. Okay, and this is really important. Okay, the elastic potential energy. Do you see the word they use here? What do they use here? EPE. This is what we use in short. EPE is what we use in short for elastic potential energy. So that is stored in a stretch string or spring is exactly equal to the amount of work done to stretch the string or spring. So do you see this is the key point here. So whatever the work done that we calculated, that work done is equal to what? The work done is actually equal. Do you see the elastic potential energy stored in a stretch string is exactly equal to the amount of work done to stretch the string. Okay, so basically what you're finding here, the work done is actually equal to the elastic potential energy stored in the string or spring. Okay. Okay, so basically the final thing is, so end of the day, the work done, but the equation you found here for work done is actually equal to what? Is actually equal to the elastic potential energy stored in the string when you stretch it. Okay, when you stretch it in a string. Okay, so EP is stored in an elastic string or spring of modulus of elasticity lambda, which has been stretched from its natural length L to a length L plus x is lambda x square over 2L. So the work done equation that you got over here, you got the work done. That work done equation is actually equal to the elastic potential energy. Okay. Okay, so we'll move on to exercise 2C. An elastic spring has natural length 0.6 meter and modulus of elasticity 8 Newton. Find the work done when the spring is stretched from its natural length to a length of 1 meter. Okay, so they're asking you to find the work done. So what is the equation for work done? Work done equals lambda x square over 2L. So lambda is given to us as how much? Lambda modulus of elasticity 8. What about the extension? The stretched amount. How much have we stretched? Natural length is 0.6. And they said when the spring is stretched from its natural length to a length of 1 meter. So when you're stretching it to a length of 1 meter, how much is the extension? Natural length is 0.6. Now the new length is 1 meter, which means the extension is 0.4. So that is x square over 2 times natural length is 0.6. How much is the answer? 8 into 0.4 square over 2 into 8 into 0.4 square over 2 into 0.6. 16 over 15. 16 over 15 joules. Okay. You could give it exact or you could give it to 3SF. If you're giving it to 3SF, you need to state that you gave it to 3SF. So if it is 3SF, it's 1.07. 1.07 joules to 3SF. That is an approximated answer. This is clear? Question number 2. An elastic spring of natural length 0.8 meter and modulus of elasticity 4 Newton is compressed to a length of 0.6. Find the elastic potential energy stored in the string. When they ask you to find the elastic potential energy, what do we know? Elastic potential energy is equal to the work done. Work done, elastic potential energy stored in the string, and the work done are exactly the same. So what do we say here? How much is the elastic potential energy or the work done? lambda x square over 2L. Lambda is 4 Newton. What is the extension? In this case, it's a compression. Natural length is 0.8 and you are compressing it to a length of 0.6. How much is the compression? 0.8 to 0.6. How much are you compressing? 0.8 to 0.6. You are compressing 0.2. Over 2 times natural length is 0.8. How much is the answer? 1 over 10. 1 over 10 joules or 0.1 joules. Okay, question number 3. An elastic spring has natural length 1.2 and modulus of elasticity 10 Newton. Find the work done when the string is stretched from a length of 1.5 meter to a length of 1.8 meter. They wanted to find the work done to stretch from 1.5 to 1.8. Okay, so natural length is 1.2. You can see to go from 1.2 to 1.5. Also, we have some work done, right? So anyway, they want you to get the work done from 1.5 to 1.8, which means what do you need to do? You have to get take the difference between the energies at those 2 points, isn't it? You have to get the difference between the energy at 1.5 and 1.8 because you can see natural length is 1.2. So the energy at 1.5 and 1.8, you need to deduct them. Which energy is higher? The 1.5 or the 1.8? Obviously 1.8, there's a higher extension, isn't it? So work done, calculate the work done in stretching the string from 1.5 to 1.8. So lambda x square over 2L. What is lambda? The lambda value is 10. Extension at, I'm going to start with the higher one. So over here at 1.8, what is the extension? 1.2 to 1.8. Can I know the extension? 0.6. Lambda x square over 2L. L is 1.2. So this is the work done when you are the work done in stretching the string from natural length to 1.8. Are you with me? This is the work done in stretching the string from the length 1.2 to 1.8. What do you do now? You now subtract the work done in stretching the string from the natural length 1.2 to 1.5. Are you with me? So what is that? Lambda is 10. What about the extension now? 1.2 to 1.5, you are stretching 0.3 lambda x square, 0.3 square over 2 times natural length is 1.2. So basically I've got the here, this is the work done to stretch to 1.8 from the natural length. This is the work done to stretch to 1.5 meter from the natural length. When you subtract, you get the work done from to stretch from 1.5 to 1.8. Okay, how much is the answer? Get each part answer separated. How do we get here? 10 into 0.6 square over 2 into 1.2. That is 3 over 2. What about the other part? How much is the other part? 3 over 8. When you subtract, how much is it? How much? 9 over 8, which is how much in decimals? 1.125 joules. You can keep it as a exact answer as well. No worries. Okay, is this clear? Question number 5. A light elastic spring has natural length 1.2 meter and modulus of elasticity 10 Newton. Let's write it down. Natural length is 1.2 meters. Lambda 10 Newton. One end of the spring is attached to a fixed point A. A particle of mass 2 kg is attached to the other end and hangs in equilibrium. Find the energy stored in the spring. Okay, so basically, what's the first thing that you need to do here? When they say there is a particle attached to the end of the spring, is it going to be in the natural length? They say it's hanging, right? And it hangs in equilibrium. That's why I drift, because it's hanging. So basically, when it's hanging in equilibrium, will it be at its natural length? Definitely no, it won't be at its natural length. So what's the first thing you need to do here? So draw the diagram. Natural length is 1.2. You have to find the extension. The question here is to find the extension. So how do I get this extension? What is the principle we use to get the extension? They say the particle is in equilibrium. If the particle is in equilibrium, forces must be in balance. So what are the forces you have here? You have the Upwards, you have the tension. Guys, the tension must be equal to what? Downward, you have the weight. What is the weight? 2 kilogram, 2g. So tension must be equal to the weight in order to be in equilibrium. Do you get me? Okay, so then let's equate them. Tension is equal to 2g. So tension is lambda x over L. Lambda value is 10 Newton. Extension is x. Natural length is 1.2 equals 2g. Shall we get the x value in terms of g first? 2 into 1.2g over 10. Can I have the value of x? How much is the x value? Let's get it in terms of g because it's not a final answer. 2 into 1.2, that is 2.4. 2.4 divided by 10 is 0.24g. Do you agree with me? 2 into 1.2 over 10. 2 into 1.2, 2.4 over 10. 0.24, you could make it a fraction 6 over 25 or 0.25. Okay, let's go with 0.24g. Okay, now what do we need to do? We have to get the energy stored. So what is the energy stored in the spring? The elastic potential energy stored in the spring is lambda x square over 2L. Lambda value is 10, x is 0.24g whole thing square over 2 times natural length is 1.2. What is the answer? So this is a matter of typing the whole thing in the calculator. 10 into 0.24 into 9.8. Whole thing square, right? Over 2 into 1.2. So answer is 23.0496. Do you agree? So you use G as 9.8. You can give the answer to 3SF or 2SF. You would give the answer to either 3SF or 2SF. So 3SF answer is 23.0. 23.0 joules to 3SF. Or you could say it's 23 joules to 2SF. Okay. Question number 6. An elastic string has natural length A. Okay. Elastic string has natural length A. One end is fixed. A particle of mass 2m is attached to the other end and hangs in equilibrium, which means this is a system that is vertically, right? It's vertically hanging. Okay, so let's draw this. So this is the elastic string. Natural length is A, and when you attach the mass, the total length of the string is 3a. Do you see it? So when you attach this mass, let's mark everything. Natural length is A. Natural length is A and a particle of mass 2m. So if the particle of mass 2m, so mark the weight. Weight is 2mg. Weight is 2mg. Is attached to the free end, hangs in equilibrium with the length of the string 3a. If the entire length of the string is 3a, what do we have to say about the extension? If the complete length of the string is 3a, what is the extension? Extension must be 2a. And then over here, you have the tension again. So that's it, right? Tension must be, so they say it's in equilibrium, which means tension must be equal to the weight. Tension must be equal to weight. Okay, let's first get the value of tension. Tension is lambda x over L. So lambda value is unknown. So you see lambda value is unknown. Extension x is 2a. Natural length is a. By the way, tension, do we know it or not? I just told you a moment ago, tension is equal to what? The tension is equal to 2mg, the weight. So you could use the tension as 2mg. Are you following me? So I can cancel off the a here and actually make lambda the subject. When I make lambda the subject, what do I get here? Lambda equals 2mg divided by 2. So lambda equals mg. So the modulus of elasticity is mg because the modulus of elasticity in this particular question is not given. They're asking you to find the elastic potential energy stored in the string. So elastic potential energy stored in the string is lambda x square over 12. Lambda is mg, x is 2a, right? So 2a square for x square over 2 times natural length is a. Mg into 4a square over 2 times a. A will cancel out. You can cancel out 2 and 4. So answer will be equal to 2 mg. Elastic potential energy is 2 mg. 2 mg, sorry, the A doesn't cancel out, right? This is 1 A will remain. So 2 mga, 2 mga joules. Guys, do you see 2 and 4 cancels? A and the A square. So 1 A is remaining at the top. So 2 mg A joules is the energy, elastic energy stored in a string. Okay. Question number 7. A particle P of mass m is attached to one end of a light elastic string of natural length A and modulus of elasticity 2 mg. Do you see what's happening here? So there is a string, a particle P of mass m is attached to one end of this light elastic string. Okay. Then they say the other end of the string is attached to a fixed point O. The particle P is held in equilibrium by a horizontal force P of magnitude 5 over 4 mg applied to P. Do you see what's happening here? This force acts in a vertical plane containing the string as shown in the diagram. Find the tension in the string. Okay, so let's get it done. First, let's mark the complete force diagram. So what is the complete force diagram? Here, OP is your string, right? O to P, you have your string. And at P, you give the force. So we are applying a force 5 over 4 mg. This 5 over 4 mg force is what's going to keep it in equilibrium. Okay, right. So you can draw these other lines. Okay, now what are the forces we have over here? Point O is a fixed point. Okay, so what are the forces we have here? Number 1, the particle P of mass m means weight is mg, weight mg. What else do you have? This is the elastic string. So definitely with the weight, you can see that it will have a tension, right? So the string has its tension. And what else? This is the natural length of the string is A. So mark the natural length. Natural length is equal to A. Okay, natural length of this particular string is A. So this remaining part is the extension. Okay. Okay, and they say the lambda value, the modulus of elasticity, lambda is 2 mg. Lambda is 2 mg. Okay, so what do we need to find here? They're asking us to find the tension in the string. Part A, they ask you to find the tension in the string. So you can see there are several unknowns here. We do not know the tension. We do not know even to find the tension. We do not know even the extension, right? Lambda x over L. We don't even know the extension. So we don't also know this angle. Okay, so these lengths are not given to us completely. So this angle theta is also unknown. Okay, so let's write what we know. Now we know this is, we do realize it's in equilibrium. So we can equate the forces horizontally and vertically, right? In equilibrium. So shall we consider equilibrium? If you consider vertical equilibrium, what do we get? If you consider vertical equilibrium, what do we get? T sine theta is equal to upwards, T sine theta is equal to mg. Do you realize upwards it's T sine theta when you resolve the tension? T sine theta, this way you get T cos theta, right? So upward you get T sine theta equal mg, and if you do left equal right, you get T cos theta equals 5 over 4 mg. These are two equations, equation 1 and 2. What is the best strategy to go here? Let's actually what? Simultaneous equation, let's divide them. Why am I going to divide? What's the advantage of dividing? You can cancel out many terms here, right? T sine theta over T cos theta equals mg over 5 over 4 mg. So you can see here T cancels out. Mg cancels out. Sine theta over cos theta is tan theta. 1 divided by 5 over 4 is 4 over 5. 1 divided by 4 over 5 is 4 over 5. So I have the tan theta ratio. Do you see? Which means now I got the t value. I actually have the the theta value. I actually have the theta value. All you got to do is, maybe we can get the sine theta ratio by drawing a triangle. We are supposed to get the tension. Tan theta is opposite over adjacent. Tan is opposite over adjacent. Can I know by Pythagoras theorem what is its length? 4 square plus 5 square square root. How much is it? Root 41. 16 plus 25, that is 41. Root of that is root 41. Which means sine theta is opposite over hypotenuse. So 4 over root 41. Do you agree with me? I'm supposed to find the tension. They're asking me to find the tension. So how do I find the tension? Let's substitute the one. T sine theta equals mg. T times sine theta is 4 over root 41 equals mg, which means tension equals to root 41 mg divided by 4. Part B, they want you to find the elastic energy stored in a string. How do you get the elastic energy? Elastic energy is lambda x square over 12. You need to find what? This extension. You need to find this extension. So how do you find the extension? We already found the tension, right? So you can write tension equals lambda x over L. Tension is root 41 mg over 4 equals lambda is 2 mg, right? In the question, lambda is 2 mg. Extension is what I'm finding, the x value. Over natural length L is, natural length is A. Agreed? Natural length is A. So now let's make x the subject. When you make x the subject, you can see mg cancels out. Agreed? So we get here x equals root 41 times A over 8. Agreed? The 2 comes down with 4. 2 times 4, 8. And here root 41 times A over 8 is the extension. So elastic potential energy stored in the string is lambda x square over 2L. Lambda value is 2 mg. Extension is root 41 A over 8. Holding squared. Divide by 2 times natural length is A. Actually, you can cancel out 2 here, 2 to 2. And you get here mg into, when you square everyone inside, the square applies to every single digit here. Root 41 becomes 41, A becomes A square over 8 becomes 64. This whole thing divided by A. So you realize that 64 is actually part of the denominator, right? Do you see that? 41 mg A square over 64 times A. This 64 is a part of the denominator along with the A. A cancels out and it's 41 mg A, 41 over 64. 41 over 64 times mg A. So this is joule. So this is the elastic potential energy stored in the string.